Hello everyone, and welcome to my talk today about introducing a next generation concept inventory using constructed response for evaluating student knowledge of complex systems in environmental education. I'm Dr. Chelsea Romulo, and I'm an assistant professor at the University of Northern Colorado in a Geography and Sustainability Studies department. So this session today is about making sense of methodologies and theoretical frameworks in geoscience education research. So in this talk today, I'll be presenting some background about this NSF grant-funded work to build an assessment tool for assessing student outcomes. And I'll talk a little bit about the methods and process that we'll be using to build this assessment tool, and then what our next steps are moving forward to hopefully make this tool available for folk and build on what we've started already in this particular grant. So just as a little bit of a background, as I'm sure a lot of folk here have also been involved with, we in my department and at my university have been doing some curriculum mapping. So trying to figure out what are our student learning outcomes and how to scaffold those student learning outcomes across our curriculum. So what classes do students really need to take, and which are the foundational classes, and what classes need to have that foundation in order to really get deeper into the material. And this is really about what do we want students to learn and how should we go about making that happen, getting that learning to happen. And you can, if you've done curriculum mapping before, you've probably seen this type of schematic where you do a little bit of backwards design, right? Identify what are our outcomes, so a student coming out of our program that is successful can do or know what. And then we need to figure out our design measures and plan for how we're going to assess that. So what are we putting into our program reviews, for example? What information are we collecting throughout the curriculum to know that our students are progressing or to find those points where there's a struggle? And then use that monitoring and evaluation to improve our program or maybe modify our outcomes. And so in thinking about program and learning assessment, we also need to think about how do we know what works and why, and that how do we know what works and why is intrinsically integrated with what do we want students to learn and how should we go about making that happen, right? How do we know what we should do if we don't know what works and why? And just as a heads up, I'm an ecologist by training, and so in my undergrad, master's, and PhD, there's a huge focus on using ecology, using ecological research in order to achieve conservation outcomes. And so with that background, that is how I'm approaching STEM education, right? What do we know about education, about student learning at a basic level, and how can we use that for the geosciences, the environmental sciences? And so when I was looking at this curriculum mapping, thinking about how my courses fit into the curriculum and what we want students to know and understand coming out of our program, I started researching what tools exist for assessing student learning. So at a basic level, we've got quizzes, exams, papers, some mix of low stakes and high stakes assessments that we can use in our programs. And then I discovered at some point concept inventories. And so if you're not familiar yet with concept inventories, the first really big one in the literature was the force concept inventory. And the goal of the force concept inventory was to assess students' understanding of the very most basic concepts of Newtonian physics, so like force, using everyday language and common sense distractors. And so what came out of this was a multiple choice response to the test multiple choice response test that was given pre and post course understanding. So students before introductory physics course would take this test. We would try to understand what they knew about force or didn't know about force coming into class, and then you would give the test at the end of the course to see what was learned. And this is an example question. So this figure shows a boy swinging on a rope, starting point A, higher, or at a point higher than A, and then think about these distinct forces. Which of the above forces are acting on the boy when his position is at A? So you can see that this is a very complex question. It's not asking to define or simply remember information, but we're applying learning, right? Those of us who create tests know that it's hard to write these kinds of questions. Since that original force concept inventory, many other disciplines have used this same method to assess learning and created concept inventories for their disciplines. One really great example is the geoscience concept inventory. I know Julie LeBarkin and Steve Anderson present at GSA frequently, so some of you may have seen them talk or know them. And that original geoscience concept inventory had 69 validated questions for introductory earth science courses, and I'll give the citation here in case you want to look that up. I will point out I've got Steve's name here in blue. He's a co-PI on my project, and so this is moving forward from the original concept inventories to how can we do something a little bit deeper. This is an example from the geoscience concept inventory, and I love this question. What did the Earth's surface look like when it was first formed? And what is really cool about these images is they're taken directly from student interviews. So these are what students were thinking before they had taken a geoscience class. And you can see that the answers are across the board, from all water, all molten rock and no water, some Pangea type thing, and similar to what we have today. And so this is really asking students to think carefully about what they know in their responses, but it's still a multiple choice assessment, so it's possible that students could guess the right answer and we wouldn't know. So what about complex integration of concepts? I teach an Introductory to Environmental Studies course, and I'm in a sustainability and geography program, and so we're really interested about how students put together pieces of information. So not just one concept, but multiple concepts together. And so this work is funded by an NSF IUSE grant, Improving Undergraduate Science Education, and this is the title of my grant if you want to look it up. And what we're thinking about is that in our environmental courses, and I'm seeing this happen frequently within the geosciences as well, there is this idea that instead of focusing just on one very specific discipline, but instead, how do we integrate concepts? So even if you're in a traditional geology class, I'm seeing folks talking about human population growth, about energy use and fossil fuels as a transition fuel. So how do we bring these concepts together and make sure that students really understand how they are connected? And before we can even get to how do we make that happen, we need an assessment tool to know what works and why. I'm going to give an example question here. This is one that we proposed in our grant proposal. This is an image. We've got the water cycle, nutrient cycles presented here. This is a very foundational concept within the integration of geological and biological cycling, oftentimes talked about in introductory environmental courses. So here's the start of our question. Referencing the above diagram, what is the significance to farmers of recycling rates in humid tropical forests? This requires students to integrate things like, what is the farmer trying to do? What are their motivations, and why are recycling rates important to them? It requires them to understand how a humid tropical forest might differ from an arid tropical forest or a forest that's not tropical. And it requires them to know something about the nutrient cycling and water cycling concepts and how those two integrate with each other. So a little bit about geosciences, a little bit about life sciences. And so when we think about the concept inventory process of building an assessment tool that looks at how students or what students understand using distractors, right? So we took what students understood from before they were introduced to information and used that to build distractors. What we're doing in my grant is incorporating machine learning into this process so that we're not using a multiple choice question, but instead we're using a complex written response. So, and I'll just say that the machine learning process also has its own system of development that we're trying to integrate here into the concept inventory process. So the way this works is we get a constructed response, and as those of us who do a lot of grading in our work, we know that constructed responses can be all over the place, and so many folks use rubrics as a way to make sure that we are assessing students consistently. And the way that this machine learning of text analysis works is the same exact way. So you can give two professors the same rubric, and if it's a really well constructed rubric, they will assess or grade constructed response close to the same, right? So we call that inter-rater reliability. But it's not often 100%, and so we're trying to work on getting as close to 100% as we can. So what this does is, or what this allows us to do using a machine learning algorithm to assess all these constructed response, is to assess students writing in large enrollment undergraduate STEM courses. Right now, this is a huge barrier to getting to this integration of complex concepts, right? Those of us who are teaching courses with 50, 100, hundreds of students in our introductory courses do not have time to grade and assess all of these constructed responses. So what we're doing in our project is we're creating these rubrics, we're collecting actual responses from students in classes, and we're feeding them into a machine learning algorithm that's going to look at the responses of students and how they're graded by multiple graders, and then constructing its own assessment, right? So this is using computer models to predict expert ratings of student responses, right? So when I'm grading this and telling the machine learning algorithm how I'm grading it, then that algorithm can take that information and grade a new response and be consistent with how I would grade it, or how our team of graders are grading. What's really, really awesome about this work is that we've partnered with a lab at Michigan State University called the Automated Assessment of Constructed Response, or ACER. This is their website, beyondmultiplechoice.org. And this is a screenshot of one of their questions that they've developed working in genetics. They've done a lot of work in creating these assessments for biology, statistics, a few different disciplines. But what they've done here is they've connected concepts into this correlation map. And so what we can do is use this same system in a concept inventory framework to say, okay, what concepts are students really connecting, and what concepts are they not connecting well? You can see in this map the thickness of the lines are where students are connecting things really well, and as the lines are thinner, that is a weaker connection. And we want to know that, right? Because we want to know where we need to bolster our understanding in our teaching, bolster students' understanding in our teaching. So right now what we're doing is we've just started this grant this month, actually. So we just had our kickoff meeting, and we're collecting syllabi, readings, assignments, lecture materials, student learning outcomes from programs and courses across the nation, and we're just about to kick off student interviews and classroom testing. And so we'll be using those student interviews to solicit responses to our questions to build our rubrics and to understand what do students know or think about these concepts before they're getting into class. And then hopefully some learning happens, right, in our classrooms, and then we can assess what did they learn, how well are they connecting these ideas. The next steps of this project are to develop and validate this assessment tool. So by the end of about 3 years from now, we will have a tool that focuses on food, energy, and water nexus concepts. At that point, we'll be wanting to move into large-scale analysis and actually answer the question of what our students are learning about these concepts in our introductory courses, and also build on our assessment tool, add more questions, and build capacity beyond just food, energy, water nexus concepts. I'd like to thank everybody for watching this short video about our project, and also give a shout out to our Research Coordination and Collaboration Network. So if you're interested in Food Energy Water Nexus education, please join. There's no cost. We have a newsletter, and we try to connect folks doing this kind of STEM education research. Again, this is part of an NSF IUSE grant, and I do have more information about the grant on my website. Thank you.